When I was younger, I had a third-generation iPod Touch, which I filled with all kinds of gimmicky apps, like iBeer. One of these apps was just a showcase of a bunch of optical illusions. It looked something like this, with a blown-up image of the illusion, a description of what's happening, a button to share it with your friends via email, and, of course, a banner ad at the bottom. But at the time, I remember feeling like this wasn't enough. The description helped me see the illusion work, but it never told me how it worked. Big problem for me. Optical illusions are a unique intersection of science and art, where our perception is tricked in clever ways. What mechanisms allow our perception to get fooled like this? And what do these images reveal about our minds and our conscious experience? Stick with me, and I'll try to answer those questions that I posed myself over 10 years ago, sitting confused staring at my iPod screen. Let's start with the most simple illusion there is. Just two lines. A horizontal line and a vertical line drawn upwards from the middle. It might surprise you to learn that these lines are in fact identical. They're the same length, but when they're positioned like this, the vertical line looks like it's definitely longer. But why? Well, consider your eyes for a second. You might notice that you have two of them. This creates a visual field that's elongated in the horizontal direction. That's why you're watching this video in 16:9 dimensions. Screens are usually designed to fit our visual field. We seem to be underestimating the size of the horizontal line since it takes up less space relative to the width of our visual field. Meanwhile, the vertical line takes up more space relative to the height of our visual field. Scientists have also tested this. They had people look at the illusion with one eye covered to reduce the influence of our binocular vision. It turned out that the illusion basically stopped working. Next, we have the famous Müller-Lyer illusion. Check out these two lines. It looks like this one, with the tips pointing out, is longer, but upon further inspection, they're actually the exact same length. The illusion's titular guy is Franz Karl Müller-Lyer, and he created this illusion way back in the late 1800s. The Italian artist Gianni Sarcone also created some really cool animations, showing off how this effect alters our perception. A close relative to this illusion is Sanders' parallelogram. A similar thing seems to be happening. You look at this figure, and the line on the left, inside the larger parallelogram, looks like it's longer, but once again, both the lines are the same length. A while ago, there was a debate about why these illusions are happening. The anthropologist Melville Herskovits figured that it was a result of our culture. People in urban western areas are always surrounded by large buildings with angular surfaces, so he believed that this familiarity affects our perception. It causes us to mistake the lengths of these lines because of the types of visual contexts we're used to. But on the other side, there was the psychologist Donald Campbell, who suggested that our perception is always pretty much the same, no matter what culture we're a part of. So the illusion is the result of more innate biases and mechanisms. To resolve this debate, they had their student Marshall Segal investigate it, which led to a paper in 1966. They studied 1,878 people, with participants from 12 different locations in Africa, the Philippines, and the US. They tested them on a few illusions, including Müller-Lyer and Sanders' parallelogram. Herskovits seemed to be closer to the truth. It turned out that the participants from more urbanized countries tended to have more responses to the illusions than the others. So it could be that these illusions are happening because we interpret the edges as corners of some bigger shape. The line that has the two corners joining in is then seen as being further away, and therefore smaller. Later, in 1978, more evidence appeared that seemed to support this so-called carpentered hypothesis. They used samples of children from both rural and urban areas in Zambia to see if the culprit is really the angular environments in Western cultures that lead to these illusions happening. It turned out that they had the same results, so the angular environment seems to be the cause. Next up, we have the Delboeuf illusion. You look at the two inner dark circles, and the one on the right looks like it's bigger. But once again, they're the exact same size. This is a lot like the Ebbinghaus illusion, where the orange circle on the right looks bigger, since you're being tricked by the surrounding circles. When the size of the surrounding stimuli is bigger, we perceive the target as relatively small. To be more specific, this is two effects happening at the same time, assimilation and contrast. Check out this demonstration of the contrast effect. The square on the right looks a lot lighter than the one on the left, even though they're the exact same color. That's what's happening with the large ring. The contrast in size causes us to underestimate the size of the central circle. The assimilation effect is the opposite. If you look at this figure from a distance, the gray background with the black lines appears darker, while the gray background with the white lines appears lighter. But if you look more closely, it's easy to see that the gray background is totally the same throughout. When the ring is only slightly larger than the circle, you overestimate its size, assimilation. And when the ring is a lot larger, you underestimate its size, contrast. Since you're interpreting both circles and rings simultaneously as one holistic image, the circles seem to be different sizes. The assimilation and contrast effects also aren't limited to visual perception. They happen all the time when we're making judgments about things. A famous example of this is Richard Nixon. Think about Richard Nixon for a second. He was famously involved in the Watergate scandal, so when you contemplate him, you might be reminded that politicians can be pretty untrustworthy sometimes. That's the assimilation effect. Your judgment of Richard Nixon is being generalized to all politicians. Now think about Barack Obama. Whatever you might think of him, he seems pretty good and trustworthy compared to Richard Nixon. Juxtaposing Obama with Nixon makes Obama seem better than he would otherwise, all else being equal. That's the contrast effect. This illusion also has an unlikely connection: food. Over the past century, the size of dinner plates seems to be getting gradually bigger, and there might be an insidious reason behind this. The idea is that when people get a plate of food, the Delboeuf illusion affects how much food they think they'll need in order to get the serving size that they're looking for. They put this to the test in a study. They presented people with a dish of tomato soup and asked them to reproduce that same quantity in another bowl, with the sizes of the bowls varying across participants. Their hypothesis was right. People poured 8.2% less soup in the smaller bowls and poured 9.9% more soup in the larger bowls compared to their target. For a long time, the Delboeuf illusion was seen as a neat little quirk of our perception, but nothing that would have any real practical value. But this study shows that illusions like this can actually reveal tendencies that impact our lives every day. And beyond that, it revealed practical strategies to overcome these tendencies. Later studies showed that people who know about this mechanism and pay close attention to it tend to reduce the level at which they overserve or underserve. The bias is still there, but it's reduced if you're vigilant, and if you know that you might not want to trust how much you think you're serving. Now, it's also important to mention that for people with eating disorders, or other cases where people need to be eating more food to stay healthy, these tips can be dangerous. Using smaller plates and bowls could just help perpetuate these dangerous behaviors. The Ponzo illusion is another instance where our perception of size gets confused. It's named after Mario Ponzo, an Italian psychologist who came up with it in 1913. He drew a set of converging lines that form the shape of a railway track receding into the distance, as if you're standing on it and looking towards the horizon. He then drew two horizontal lines on the scene, which are completely identical in length, but they don't appear that way. At first glance, the top line looks longer. This is happening because we're interpreting the converging lines as a three-dimensional scene. The way the lines are organized gives the illusion of depth and distance in the scene. The top line looks like it's further away, making it seem bigger than the bottom line, which looks like it's right in front of us. This also works with just two converging lines, or with other objects other than lines. Our brain is trying to make sense of the scene in 3 dimensions, so it compensates by adjusting the perceived size of the two lines relative to how they would be in that environment. The Zöllner illusion is a chaotic image of diagonal lines, with regular intervals of intersecting lines. It kind of reminds me of stitches, or zippers. It actually wasn't discovered by a psychologist at all, but by an astrophysicist. You might not notice it at first, but the small intersecting lines are actually perfectly horizontal and vertical, alternating on each diagonal. In fact, all of the diagonal lines are perfectly parallel. These small intersecting lines are doing all the work here in tricking our perception. Let's isolate 2 of the diagonal lines for a second. The tiny lines seem to be giving us the impression of depth, as if one end of the diagonals is closer to us than the other. If there was depth in this scene, we would expect those diagonals to be converging towards each other on one end, and veering away from each other on the other end. This is why our perception is getting confused, and the diagonal lines don't quite look parallel. In 1973, Steve Simpson was working at a psychology lab in Bristol. On his way to work, he passed a café with an interesting tile pattern. He brought this to his colleague at the lab, Richard Gregory, and they realized that they had found a real-world example of an optical illusion. A similar illusion had been discovered long before, in 1894, but this version was particularly effective. It looks like the stacks of bricks are askew, with the rows chaotically sloping into each other, but all the rows are perfectly parallel. The illusion works in part because of the offset positions of the black and white tiles, but also because of the thin gray borders between each row. The gray dividing line happens to be between the luminance of black and white, which is important. If the dividing line is white or black, the illusion seems to stop working. Often, when we're making sense of spaces and surfaces, we take advantage of transitions in luminance to make sense of where the edges are. The relevant section is the in-between space, where the black tile sits above the dividing line and the white tile sits below, or vice versa. Here, in this in-between space, the black tiles almost want to lock onto the black tiles in the adjacent row, and the white tiles want to do the same. The narrow gap of the gray dividing line allows us to almost follow through on this locking in process, because of the comparatively neutral gray stimulus. The next illusion involves a red herring, something that distracts attention from the real issue. But this herring is spelled with one R. In 1861, Ewald Herring drew this scene, with a bunch of lines emanating from the edges and converging into a central point. He also placed 2 red lines next to the center. But those lines don't quite look like they're straight, do they? They almost look like they're bending outwards in the middle. The explanation for this illusion is pretty wild. When we perceive things in the world, we're basically looking into the future. We're not exactly Nostradamus levels of clairvoyant, but we're looking at the world about 1/10 of a second into the future. This is because of the mechanisms of our visual perception. Light hits our retina, and there's a lag of about 1/10 of a second before our brain is able to translate that information into what we see. It's a small delay, but it's an important delay. The cognitive scientist Mark Chongizi has suggested that we actively compensate for this lag, and our brains generate images, not just of what's happening, but what will happen 1/10 of a second into the future. This makes sense when you consider how fast-paced the world can be, and how fast our ancestors had to respond to the things they see. When a venomous snake could start charging towards you at any moment, every 1/10 of a second counts. Chongizi argued that this actually explains a lot of optical illusions, including the herring illusion, and some of the others I talked about already. The radial lines in this illusion are special because they're the same pattern that we see when we move forward. When we're moving forward, something called optic flow happens. The objects in the scene leave trails on our retina as we pass them. This is why cartoonists and animators leave these blur lines in to create the sense of something moving. You're walking towards a door frame, and in the first moment, the sides are perfectly parallel, but as you get closer, they actually start to bend outwards a bit. If we take out the radial pattern, the parallel lines look totally straight. There's no indication that anything is happening, or anything is moving, so your brain just takes it as it is. But once the pattern is introduced, your brain figures that you must be moving forward. It conjures the future perception of the next moment when the vertical lines would begin to bow out. The Müller-Lyer illusion from earlier might involve this effect to some degree as well. The outward pointing lines seem to fit more closely with the pattern of optical flow as you move forward, towards the line. But the lines pointing in seem to fit the optical flow as you move backwards, away from the line. As your brain anticipates the next moment, it expects the line on the left to be closer, and therefore bigger, while it expects the line on the right to be farther, and therefore smaller. Okay, I think that's enough about misjudging sizes. Let's move on to a whole new type of illusion. Despite all the mistakes I talked about earlier, humans are usually pretty good at interpreting visual information. We can look at a 2-dimensional image on paper, or a computer screen, and interpret a 3-dimensional figure, like the famous Necker cube. This is just a bunch of connected lines. It's 2-dimensional. But we don't see it that way. We see a box. But because of how simple the figure is, there are actually 2 different ways you can interpret it. You might see the lower left square as the front of the box, or you might see the upper right square as the front of the box. Chances are you saw the lower square as the front, which is the most common way of seeing it. This might be because we usually encounter objects in the world from above, rather than from below. But notice that you can see it both ways, swapping between each interpretation seamlessly. But you can't see it both ways at the same time. Both of the interpretations are perfectly correct because the drawing is ambiguous. This type of ambiguity allows for a specific type of illusion, impossible objects. This is the Penrose triangle, a classic example of an impossible object, which seems to be representing a 3D shape. It was originally created by the artist Oscar Reuterswald at age 18, who made loads of really cool pieces taking advantage of impossible figures. This one is called the Penrose Triangle because it was later invented independently in a legendary paper by a father-son duo, the psychiatrist Lionel Penrose and the Nobel Prize-winning mathematician Sir Roger Penrose. When you look at the shape and follow along its surface, your perspective and interpretation suddenly shifts. You can also get much more sophisticated with this sort of thing, like this shape from the Penrose paper, with a more intricate pattern of overlapping surfaces that forces you to reassess your interpretation way more often. The Penrose stairs illusion was described in the same paper, and it was also independently discovered previously by Oscar Reuterswald. You look at each section independently, and it looks like a perfectly normal flight of stairs. But the way that the steps meet makes it impossible to interpret this figure coherently as a whole. The steps continuously ascend and descend in each direction. A year after the paper was published, M.C. Escher created his famous work Ascending and Descending in 1960, which included a similar kind of never-ending staircase. The illusion is taking advantage of the vertical position of the steps. Remember the Ponzo illusion from earlier? We use cues to determine depth, and objects that are higher up seem to look further away. When you look out at the world normally, your field of view extends from the ground below you, up to the sky above, and ahead of you, with the horizon about midway. Objects move towards the bottom of your visual field when they approach you, so objects that are higher up are usually further away. M.C. Escher used this type of figure again in his 1961 piece Waterfall, where the looping structure creates a perpetual motion machine. The water falls down, and then flows through the stream, leading back up to the original waterfall. This shape is essentially just two Penrose triangles combined together. Impossible objects are also an example of what Douglas Hofstadter calls a strange loop, which is a concept he coined in his legendary book Gödel, Escher, Bach. Strange loops are pretty trippy. They're basically a series of stages that you follow from one level of abstraction to another, like one step in the staircase to the next, where it feels like you're moving up to the next level in a hierarchy. But at some point, the loop closes. You go up the next step, and you end up right back where you started. A succinct phrase I like to use to describe it is an infinite circular hierarchy of self-reference. Some other examples that Hofstadter talks about include music by Bach, the self-reference in Gödel's incompleteness theorem, and even self-consciousness itself, hence Gödel, Escher, Bach. The impossible cube is another famous impossible object. It's sort of like the frame of a Necker cube, with visually overlapping edges. This is using the structure of interposition, where some bars cross in front of others in spatially impossible ways. The pillars are depicted in such a way where one pillar is both behind and in front of another pillar simultaneously in different regions. Once again, M.C. Escher used this type of thing too, in his print Belvedere. You might have seen this bizarre shape before. The impossible fork. At the tips, it looks like it has three distinct prongs. But as you shift your gaze back to the base of the fork, it's actually just two prongs. The edges of the prong tips are used to form what appears to be a two-pronged three-dimensional structure at the top. These kinds of illusions work because the figures seem to depict coherent shapes in local regions, like the prong tips by themselves, or the base by itself. But it defies spatial rules globally when you look at the figure as a whole. There are also figure and ground illusions, like the shepherd's elephant. The legs of the elephant stretch down into nothing, while the feet are attached to parallel leg shapes generated by the edges of the elephant's legs. I found a few other illusions that use the same mechanism. Here, in the middle section, the figures and the ground are reversed. The black background suddenly shifts to legs and feet. There's also this lumberjack in a forest, which seems like a fairly normal scene at first glance, but it's actually impossible. The top sections of the trunks don't line up with their respective lower sections. They're each shifted one place to the left. The artist Shigeo Fukuda also used this effect in a few of his paintings. The most famous example of the figure ground illusion is Rubens' vase, which can be perceived as both two faces staring at each other, or a vase. Just like the Necker cube, this image has two interpretations, which are entirely consistent with what you're seeing, but you can only see one of them at a time. Depending on whether you see the white or black figures as the object, the other figure in the image will cease to be a figure at all and sink into the background. The two interpretations share the same border, so it's impossible to see both interpretations at once. If you try to make sense of the image as a whole, the figures contradict each other since there's no background. This kind of visual ambiguity is also at play in the spinning dancer, aka the Kayahara silhouette. It was created in 2003 by the computer graphics artist Nobuyuki Kayahara to show off a new web graphics tool that just came out, Macromedia Flash. The weird part of this animation is that you can see the girl spinning clockwise or counterclockwise. Your perception can change spontaneously, even though the animation is the exact same. People have even created illustrated animations that make it easier to find cues that allow you to swap the spinning direction. This is possible because the original GIF is a silhouette, so there isn't any information to discern visual depth. In the first interpretation, you're looking at the girl slightly from above. She's standing on her left leg, bending her right arm away from her body, and she spins clockwise. In the other interpretation, she's seen slightly from a lower perspective, standing on her right leg with her left arm pointing away from her body. Here, she spins counterclockwise. Without any cues, most people see the figure spinning clockwise, which is the way I see it by default as well. According to an online poll from a popular science blog, about 2/3 of people see it spinning clockwise. It actually ended up being used as a bullshit personality test that would supposedly show you whether you were left or right-brained, and that the way you interpret the spinning direction is related to your hemispheric dominance. There's a good chance this happened because people didn't really know why they saw the GIF in different ways. So why do most people see her spinning clockwise? Well, it implies that people interpret the observer as being slightly above the dancer, looking down on her. This is the exact same phenomenon as the Necker cube, where most people see the lower left square as the front, because they intuitively assume that they're viewing the object from above. But it also goes deeper. The GIF contains a shadow cast on the floor. As the figure rotates, the shadow gets closer and moves away from the figure, as you would expect it to, which indicates that the floor is horizontal. If the floor is flat, and we see the shadow below the figure, then that means that we must be looking down at the figure, and it should rotate clockwise. But the movement of the shadow is the complete opposite. If we track the motion of the shadow, it's moving counterclockwise. This makes the GIF doubly illusory, because it's both a reversible figure and an impossible figure, like some of the other stuff in this section. The motion geometry is coherent locally when you look at only the figure, or when you look at only the shadow, but together in a global sense, it's impossible. The next type of illusion makes you see things that aren't there. This is the most famous example, the Knizia triangle. 3 Pac-Man looking guys are placed around 3 sets of converging lines. With these shapes arranged just so, you'll notice that they form a triangle. The triangle has no real edges or change in illumination relative to the background, but we still see it. It's almost like the triangle is a bit brighter than the background, but it's all the same shade of white. You can create this effect with loads of different patterns. These blobs that almost look like the new Patreon logo seem to want to connect, and you can almost see the edges continue to form an S shape. This collection of cones and triangles, when taken together, look like they're attached to a cohesive 3D ball. The ball has no edges, and yet we see it. These abstract shapes look kind of like a snake swimming through the water, and you can almost notice an edge where that horizon line should be. The Ehrenstein illusion is another example. A radial pattern of lines form the shape of an illusory circle, which appears to have a defined edge, even though there isn't one. In my case, these phantom shapes are easier to see when the cues are more complex. In this image, a set of nested circles abruptly shift from black to cyan, which forms the structure of a larger circle in the middle. If you squint, it looks like the circle is a clearly defined shape, when in reality it's an illusion formed by the patterns of colors. This grid creates a similar effect, where the intersection points are drawn in a light blue shade. The contrast in color forms the shape of tiny blue circles at each intersection point, even though all the lines are perfectly straight. This chaotic entanglement of lines does the same thing. Within the confines of a circular area, all the lines become blue. This generates a perception of a circle, with illusory edges and a bluish-looking color. The background of this area is clearly white, but with the full context of the scene, it almost appears faintly blue. These phantom shapes don't really have a clear-cut explanation, but one suggestion is that it can be accounted for by Gestalt principles, specifically the law of closure. According to Gestalt psychology, we don't just perceive individual components on their own, but also full patterns and configurations of those components. The whole is usually more than the sum of its parts. Our mind is tuned to see certain familiar patterns, like basic shapes. So if there's information missing, we tend to fill in the gaps and assume that the shape is completely enclosed. The final category of illusions I'll cover in this video is probably the most remarkable: stuff that moves. This is the most simple form of the peripheral drift illusion. Here we have two grayscale pie-looking structures, with a gradient in each slice. If you blink, or I flash these shapes on your screen, they might seem to be rotating. The optical illusion legend, Akiyoshi Kitaoka, created an optimized version of this illusion that seems to work a lot better, as well as versions in color, which seem to work the best. Akiyoshi created a bunch of different illusions based on this drifting phenomenon. His most famous is his rotating snakes. As your eyes move around the image, you'll notice that each of the spirals seem to be rotating. Akiyoshi's primrose field involves a checkered background of squares with colored shapes at their vertices. The image appears to wave, as if it was a piece of fabric in the wind. His piece called Rollers seems to roll around. And his coffee bean illusion might look familiar if you're a music nerd. This pattern inspired the cover art for the Animal Collective album Merryweather Post Pavilion. There are a few ideas for why this drifting is happening. The most compelling of these is also the most intuitive. It seems to have to do with eye movement. If you keep your gaze as focused and still as you possibly can, the illusion is greatly diminished, but if you move your focal point around, it's enhanced. According to this model, there is, quote, asymmetry in strength of motion signals depending on the direction of a moving pattern on the retina, and illusory motion arises from a difference of motion signals provided constantly by miniature eye movements. A similar type of motion illusions are what's called scintillating phenomena. Don't worry, I had to look up what that word means too. It's lively or stimulating. It's been used before in op art, like The Fall by Bridget Riley from 1963, or the Enigma illusion. It looks as if these images seem to shimmer, even though they're totally still. This category of illusion is the result of eye movement too, but specifically the subtle ones. Even when our eyes are perfectly still, our eyes are still making tiny, unconscious adjustments really fast, which are called microsaccades. There was a study where participants had their microsaccades suppressed, and it turned out that the images stopped flickering entirely. They were perfectly still. Another related type is sliding phenomena, like the Uchi-Spillman illusion here. If I shift this image around a bit, the sphere-looking shape in the center seems to separate from the background and create this sense of dimensionality. It's as if the sphere is a real object in front of you, sliding around on your screen. The pinna illusion takes advantage of this too. A black dot is surrounded by two rings of squares, each formed by white and black edges. If you move your head forward, or I slowly zoom the image in as you gaze at the center dot, the rings of squares appear to rotate. The inner ring counterclockwise, and the outer ring clockwise. If I zoom out, the direction of rotation is reversed. The illusion only happens in your peripheral vision, when you fix your gaze in the middle. If you look at one of the squares on the edges, it stops working. An interesting part of this illusion is that the speed of rotation is directly proportional to how fast or slow the image zooms in or out. Kitaoka's so-called spine drift illusion is another example. The image is filled with an array of spikes, with a gap separating a square in the middle. You might notice that the square seems to be floating or moving relative to the background. If I shake the image a bit, the illusion is also enhanced. All of these sliding illusions involve microsaccades as well, like the previous category, but they're also caused by what's called retinal slip. In these cases, the images are actually shifting on the surface of your retina, which gives the impression that they're sliding around. The last illusion I'll touch on in this video is a bit different from most of the others. Rather than being induced by abstract shapes or illustrations specifically designed to trick you, this one can happen to you in perfectly ordinary environments. When you stare at a moving pattern, like a waterfall, for an extended period of time, and then look away at a still surface, you can experience the illusion of motion in the opposite direction. I've experienced this before while gazing out the window of a moving car and keeping my eyes fixed on the pavement as it rushes by. When the vehicle stops, the pavement appears to move in the opposite direction. The first person to describe this effect was actually none other than Aristotle in his On Dreams treatise, where he described experiencing this effect after gazing at a flowing river. In lab settings, you can induce this kind of effect with patterns of moving black and white lines, or spirals. If you stare at the center of these kinds of patterns, and then look away at a wall or something, it results in a brief motion after effect. The reason this happens is pretty intuitive. When you stare at a constantly moving thing, whether it's a road going by, a waterfall, a river, or an abstract animation, your neurons end up adapting to this pattern. When you take away the movement, your brain has adapted to the motion, so it has to reset back to normal, which can take a couple seconds. This was shown in a classic paper by Barlow and Hill in 1963. They recorded the neural firing of a rabbit's retinal cells and then stimulated their retina with movement. The firing of the cells increased with the movement, and then over time, gradually decreased. The rabbit was becoming accustomed to the movement. When they took the stimulus away, the rate of firing fell way below where it started before the movement, and then it slowly recovered back to baseline within a few seconds. This is neural adaptation, and happens with pretty much any kind of perception. When you put on a t-shirt first thing in the morning, you physically feel the fabric sitting on the surface of your skin, but after a few seconds you adapt to that sensation, to the point that you barely notice it. I hope that my younger self would be satisfied with the explanations in this video, when he sat staring at illusions on his iPod. He would probably wish that the explanations were simpler, or more conclusive, but what are you gonna do? Unfortunately, there's no true unifying theory of illusions. The types of images that trick us vary considerably, and they take advantage of different mechanisms. But there's one idea that ties them all together. We are animals. We don't see the world exactly as it is, like a mirror image. We're always engaged in a process of trying to make sense of what's around us. We try our best, but we're imperfect. And sometimes what we see is not quite what there is. These lines are the same size. There's no triangle here. This isn't actually moving. Our sense-making is tuned to certain patterns and is steered by our biology. We see 1/10 of a second into the future. Our eyes dance around. Our peripheral vision is just filling in the gaps. Our sense-making is powerful, and it has its limitations. But despite all this, what we see is usually pretty close to the truth. I hope you enjoyed the past half hour or so. While I have you here, I have a quick plug. I recently created a Patreon for those who enjoy my videos and want to support me. If that's something you're interested in doing, there's a link below. You'll get some nice perks, including access to bonus videos, extra content, and early access to new videos with no ads. There's already a bonus section of this video, with more illusions on there right now.